All right. Can you guys hear me? Sounds like it was working. I'm going to go ahead and get started. So my name is Patrik Sundberg. I'm going to be talking today about machine learning as applied to FHIR. My talk today will start out by first reviewing a bunch of recent advances in machine learning in general, which then leads us to how can we apply those machine learning advances to healthcare, and some of the work that we've done in that space. And then how can the community in general take advantage of these things, for example, using some of the open source tools that we've made available. And so let me start first by going through some examples of machine learning that are all fairly recent, in the sense that they're in the past couple of years. People have worked on machine learning for a long, long time. Neural networks, for example, date back to like the 80s or late 70s even, or even before then. But it didn't really work until maybe 5-7 years ago. And so one of the first things that really truly started working was image recognition. So here are some examples of actually recognizing objects in an image. So this is from the ImageNet database that has over 1,000 categories of things. And the system is actually able to, and this is 2 or 3 years ago, is able to recognize animals with a precision that's equal to or even better than humans. And so, for example, unless you know a lot about lizards, you might not be able to distinguish these two particular ones. But the computer has no issues with that. And a thing that happened soon after the models were able to handle these images is people started to be able to use these things in their own applications, like real estate applications or other things, to classify things that are useful for their applications. And so that took just a few years, and that's kind of where we're hoping to get with healthcare as well. Another thing that happened that I think a lot of people saw was DeepMind in London. They spent a lot of time working on Go, which is a lot more complicated than chess. Chess sort of, we got to human level performance with computers in the 90s, but Go, people thought it was going to take much longer because the game just is so complicated. There's a lot of different positions. And similarly, self-driving cars. And here you're getting to an example where there's a lot of different components that use machine learning in a system. For example, recognizing things like street signs and stoplights and pedestrians. And they all work in concert with the overall system. And really, machine learning is just a tool that helps you get some of the things that you need done. And it's a part of the overall system. But machine learning can also be used for things other than just detecting. And for example, it can be used to generate images. So what would happen if you take the United Nations building, for example, but you were to render it in the style of Picasso? And so it turns out you can do that, and it would look roughly like that. And so this is done by a tool called Neural Style, which, again, you can Google, and you can go and put in your own images and render yourself in the style of Van Gogh or something like that. Similarly, what does the system actually see when it makes these predictions, the image predictions? So here is something called Deep Dream, which attempts to sort of run the model backwards, saying that here, for example, you see a castle in this image, highlight everything that looks like a castle, and tweak the image a little bit so it looks a little bit more like a castle. And so if you run that roughly, then you can see that sort of, you see kind of what it's getting at in images, and it's an interesting insight to what the model is actually doing. And on your phone today, even, you can use some of these tools, combine, translation and image recognition and whatnot, which actually turns out to be pretty helpful when you're out traveling, for example, and want to look at menus and things like that. And so what's making these advantages possible? And so there are really two main things. One is the software has really gotten a lot better. And so Google's version of the deep learning software is called TensorFlow. It was open source back in 2015, and it's used in production at Google and elsewhere, and it's also used in research. So typically, the most state-of-the-art algorithms that exist, there are TensorFlow implementations of them. There's a very vibrant community contributing and using this repository. Similarly, hardware has also taken great leaps forward, right? So CPUs were getting faster, and then people started using GPUs because they're actually suitable for machine learning. And then people got to the point where actually, if we special purpose design for machine learning, can we do even better? And right, and so this is the cloud TPU, a tensor processing unit, which was released earlier this year. And so it's a 180 teraflop device. And in fact, you can bundle them together and create like a 10 petaflop device, right? And so, or 11 petaflop device. And these things are available today, which is ridiculous if you just think back, a couple of years ago to what computing was like. And so you can train much bigger models on much more data. And it turns out that the amount of data that you use is really maybe the most important factor in how well a model performs. All right, so how does this all help us in terms of healthcare? And so fairly naturally, some of the first applications, even in healthcare, have been image related. So this is the work of one of our sister teams at Google, who's looked at diabetic retinopathy. And so diabetes obviously is a very common condition, and one of the most common side effects in especially the developing world of diabetes, if it's untreated, is blindness. And so what people do for this is essentially trucks will drive around, or not trucks, but like buses will drive around into little villages in like India and Tanzania, and they will screen people by taking photos of their eyes, and then they'll upload them to Dropbox, and then someone in Mumbai will look at the photo and say, this person needs treatment. And then you have to go back to that village and find that person again, because this could be a round trip of a day or 2 days or something like that. And so this is obviously, there's a lot of issues with this. And so the question was, can you do this? Can a computer do this as well as humans, or better? And so it turns out that the answer is yes. And over the past years, the team has been working on this and getting better and better. And as of this year, they're as good as retinal specialists, which actually means that the computer is probably better at grading this than even the doctor that you would see in the US if you go and see, or in Europe if you go and see a doctor for screenings like this. And in addition to that, so this model also, here the green is showing what does the model look like to make the predictions that it's making. And so we see that it can, well, first of all, it can predict things that humans didn't think was possible. So for example, you can look at a retina and predict the gender of the person with 0.97 AUC. And it's looking at those green spots in the image when it does it. And it doesn't necessarily help us to see. This is like explaining what a model does is really hard. Even if you know where it's looking, you don't know what it's looking at those positions and why it's important. And maybe if you're a professional, you would know. But I think in this case, actually, it doesn't really help you that much either. It can also predict the age of the person based on the image. And things like blood pressure and other risk factors for cardiovascular disease. And so then follow-up question then is, can you actually predict cardiovascular risk? And it turns out you can roughly as accurately as a blood draw, like from just a picture of the eye. And so one of the reasons why you might think this might be possible is the eye is the only part of the body where you can actually really see blood vessels and neurons with an image. And so there is that potential there. And so it's an interesting area for future research. All right. Okay, so this is all great, but what does that have to do with FHIR? And so we're here, or I'm here, and a bunch of other people on my team are here because we've looked over the past few years at medical records and trying to apply some of these same advances to the field of medical records. And so as you all know, you start out with a very complicated data model. If you look at an average EHR, you might have thousands of tables. And that's just the beginning of it. The terminology, it's very complicated, and there's just a ton of different issues. And so where do you even start? And so where we started was we were trying to normalize first sort of the structure of the data. We need to try to find a way that different data sets from different hospitals can be put in a uniform format where the models can then sort of share learnings, for example, across different institutions or different tasks, things like that. And FHIR was clearly the natural representation here. We looked at a bunch of other things in the beginning as well, but pretty quickly we settled on FHIR and trying to make FHIR work. And that's proven to be a good decision. And so roughly, how does that work? So as a first step, we start with the EHR data. And then we map to FHIR resources where, for example, we go and find the things that are observations, the things that are medications, and try to put those roughly in the right place. And here, we don't really address, at the first step, the actual terminology. Do we need to know that lab code 12345 is like glucose measurements? We do not yet at this point, right? And so we don't necessarily do all of that. We focus on the structural mapping. And this is really where FHIR is quite good at being able to express all the things that we need. And it was nice that we were able to take advantage of several years of work that the community has put in order to get these data models to the state where they're at today. And then once the data is in FHIR, now we need to massage it in some way so that we can use it as input to TensorFlow. So TensorFlow typically has a few standard inputs that looks like FHIR is not one of them, that it likes to use. FHIR is not one of them. So we need to sort of bridge that, and I'll talk more about that later. But one of the key things here that we focused on was really ordering all the events that happen to a patient on a timeline. So the model can start reading from the far past and go forward. And as it gets to more recent things, it will probably look at various values, for example, with a different sort of mindset, if you will, to see, for example, if you had a heart attack 5 years ago, that might matter less than if you had a heart attack yesterday, right, for various predictions. And so when we model this, we essentially copy the FHIR data model to some extent. We pull out all the FHIR resources, and all the features are essentially corresponding to elements of the FHIR data structures. And so you end up with a representation that kind of looks like this, where you might see, for example, encounters, labs, medications, as they go over time. And because we use a sequence model here, we're able to accommodate a variation in record length, variation in whether some data is present versus not in various EHRs. And we're also able to just take the notes, the clinical notes, the text, and just put them in as they were. So the model itself can deal with the text in whichever way is appropriate for that specific task. And so you end up with a timeline where each dot here really corresponds to one FHIR resource. And there's different numbers of them across time. And then we need labels. So using this, we try to predict things like, is this patient going to get readmitted after they leave the hospital? What's the ICD-9 code, ICD-10 codes? What's the glucose level? Things like that. All right. And so one of the differences using this approach compared to what was done before was we actually use all the data now, right? And so it could be hundreds of thousands of data points for a single patient, whereas before, typically, the standard model only used roughly 27 variables on average. Things like what's the average glucose, what's the average, how long has this encounter been, things like that, hand-coded features. And so here we're able to actually use all the raw data and all the power that comes with that. And so earlier this year, we published a paper on our work here, which talks both about the way we represented the data and the models that we used. And so if you're interested, you can go and look up the paper. And we showed that the approach that we took was better than the state-of-the-art at the time, and in various different tasks. And I think one of the reasons, obviously, is that the deep learning models that we used are more powerful than the things that were used before. But another reason is we were able to use more data, right? We were able to use features that were not used before. And so it turns out that the models pick up on various strange things sometimes, things that you would never think about hand coding. For example, so our model is also the type that pays attention and shows highlights where in the record are the important things for this prediction. So in this particular case, we have a mortality prediction where we're trying to predict, is this patient going to pass away in the hospital during this encounter? And so the features that are important according to the model are highlighted in red here. And so one of the things that I'll bring up here is this word plurix, which is, I don't know if anyone knows, but that's apparently a brand name for a catheter that you typically only use on patients that are essentially, that have a specific type of cancer and are almost certainly going to die in the next few weeks, right? And so this feature is clearly very strong because it includes judgment that's made by the clinicians in a way that's very subtle, right? And so a model will pick up on these things, whereas if you hand code features, you would never think of doing that. And so what can you actually do if you can do these predictions better, right? So one thing that you can do, which I think all clinicians would love, is you can reduce the number of alerts. Alert fatigue is one of the most common complaints and causes of just people ignoring actual alerts in hospital because there's just too many. And in addition, if we're actually able to detect things 24 hours sooner than the existing models, and so clearly that has a lot of clinical implications as well. If you can predict things like sepsis or something like that 24 hours earlier, you can actually do something about it. All right, so how would I go about and use these type of advantages in my application? So one of the things that we did from the very beginning was we wanted to open source some of our work with the same motivations as open sourcing TensorFlow. And so we have a GitHub repository that we've put code on over some time. And now most of the stuff that we've done for the machine learning stuff is also there. So I'm going to walk through that a little bit. There's some stuff that's not yet there and will probably come out along with follow-up publications, but there's enough to definitely get started. And so there's more than the machine learning parts in this repository, and Nick will tomorrow talk about some of the other features that, in particular, the protobuf implementation of FHIR that we use internally, that's helpful for other things than just machine learning. All right, so let's take a step back and think about machine learning, sort of the phases of actually deploying machine learning in an application. And so at a high level, first you have to get some training data and train a model. And that involves various sub-steps. But once you have that model, now you can apply that model on your real-time production serving data. And I'm going to talk about that too. But first, let's talk about sort of how the model gets created, and then about how that model that was just created in the training phase is used for inference of serving. And so since this is a FHIR conference, I assume that people know how to get some data to start with. It's not always actually obvious, but if you have data in FHIR, the representation that we've started with for our machine learning task is always take all the data for all the patient and group it together. So create one bundle with all the information from the patient. And you can see why we do that, because it corresponds roughly to the timeline that we're going to create later. And there is actually an operation in the FHIR spec that's pretty similar to this, the patient get everything bundle, which is in some ways a model for what we're doing here. And then we have to decide exactly what we're going to predict and how. And so there's really 4 questions that you have to start answering when you're thinking about applying machine learning to a problem. So first, what at a high level are we predicting, right? Who are we predicting it for? And that's the cohort. And then at what time are we predicting? Because that could actually influence the task in various different ways. And then what's the actual value of the thing that we're predicting for the specific patient at the specific time? And so one of the main labels so far that we've open sourced in this package is the length of stay label. And so a length of stay prediction task is essentially you predicting when is this patient going to leave the hospital. And so who are you predicting it for? you're predicting it for someone who's an inpatient, someone who's admitted to the hospital. And in our case, we're saying we're predicting it for someone who's been in the hospital for at least 24 hours. And so when are we predicting it? And we're going to predict it 24 hours after admission. And the reason for that is, well, first of all, part of our cohort is restricted to people who have been there for longer than 24 hours. So we guarantee that everyone in the cohort will actually be there at that time. Second, there's usually a bunch of measurements that are made pretty soon after admission that actually will end up being helpful for a length of stay prediction. And you roughly have, at a high level, you have most of the things that you need after around 24 hours. And so then what is the actual label? Like what is the thing that we're predicting? And so we've decided in this case, we're going to bucket the length of stay into 4 different buckets where you're going to stay at either between 1 and 3 days, 3 and 7 days, 7 and 14 days, or longer than 14 days. And so this is one example of a prediction task, which is like a pretty standard thing. But all these questions have to be answered for any task that you're interested in doing. And so given these tasks, we're going to create essentially a label. And so we have an extension for event labels, which is part of the open source package as well. And this is roughly in like pseudo FHIR how that extension looks like, where I've shrunk it so that it doesn't use all the verbosity of an actual extension, but this is roughly what it looks like. And so you can see that there's a few key fields in there. And so how would you actually go about generating this? So some people prefer to actually use code. And so you can look through a bundle, for example, and you can find out where are the encounters for this patient, and does the patient qualify based on some conditions. This code also is from the GitHub repository, where we have a Beam Python job that runs on bundles and produces labels of the length of stay kind. And you can change the boundaries of the buckets if you want and add more buckets, and you get a slightly different task. If you don't want to use code, sometimes you can actually use just SQL. Right? And so again, this depends a lot on your task. So this task is a different task where you might want to look at the observations that you've now loaded, for example, let's say into BigQuery or some other engine that supports SQL. And you extract the fields that you care about, including the cohort and the time, just by a simple SQL query. And so here, for example, we might say that if the fasting glucose, which that line code corresponds to, is greater than 130, then we're going to say high. Otherwise, we're going to say normal. And obviously, I think a lot of people here probably will have some comments about that specific label definition. But that's the thing, again, about label definitions, that it depends really on what you're trying to do, and it's tricky to get it completely right. And in some you have to actually generate a label using something that's a lot more manual, which is chart review. And this could be the case, for example, if the information that you need isn't easily expressible or isn't in the record at all. And so it could be implied, for example, was the patient on a ventilator, and if so, when did that start? And sometimes that takes a little bit of manual effort to look through the records. And so these labels are obviously more expensive because they required skilled labor to find out, but they can also be used. All right, and so once you have the labels and the FHIR data, now you just need to generate examples. So in the open source package, this is the binary that you'd run to produce the TensorFlow sequence examples. And so this is the definition of TensorFlow sequence examples. Basically, they're protocol buffers that contain the features that you need. And I think it's probably easier to actually look at an expanded example, right? And so here, as I mentioned earlier, each field in each resource becomes its own feature. So here, for example, in observation, you have observation.code and observation.value, like value quantity, basically. And there are, for each time step, there's going to be one feature in the list. And they need to match up, essentially. They will match up time step-wise. So the first feature in observation.code happens at the same time as the first feature in the value quantity. And if you have something like a note, all the words in the note are actually just concatenated in essentially this list. If you don't have a feature as a specific time step, then that list is just empty. So like, for example, if there was an observation at this time step, but no composition, then that composition would be empty at that time step. There's also a special feature list that tracks the timestamp of each event explicitly. And so the model can look at that to see how long ago this event happened. And then there's a small number of context features that are global to the example that essentially just are shared. So for example, patient.birth date. So in this case, sometime before 1970, that doesn't change, it's just always the same. The label is also a context feature. So in this particular example, the label is a length of stay above 14 days. And so once you have your examples, now you need to build a model and train it. And so we've put in our package an example Jupyter notebook that trains a linear model, but that uses time-bucketed features. So there's really a cross of the feature with the time when it happened. And so you can play around with that and see roughly how that works. It's a very simple model. But I think the point here is we've open sourced the tools for creating the examples, and that really opens up the ability for someone to just focus on modeling and open source a TensorFlow model, for example, that can then be used on examples of this type. And so we expect more models, and if, for example, anyone here is interested in writing models, then they can easily be open sourced and paired together with these examples. It's really one thing that was missing in the past was something like in the image world, like libjpeg, for example, turning the FHIR data into something that is actually parsable by the machine learning input. And so now that that exists, a lot of other things will be easier to do for people. And so here's, again, how you would train it. And so I don't want to focus too much on this because there's a lot of little technical things in here, but the high-level point is that the models are there in the packet, and other models will be added soon. And so I do want to focus, though, on one little property that's actually quite important about how many of these models works. And so one key feature about the way this works is you don't necessarily need to harmonize all the lab codes. You don't need to know all the time what lab code 1, 2, 3, 4, 5 actually means. You need to know it if you're going to create a label from it. But if you're just using it as a feature, it doesn't actually matter whether you have the long code for it or the ICD-9 coded, or you just have the raw data from the table. And the reason why is we're going to embed this into a higher dimensional space. And so embeddings are essentially, you can think of it as you take each token and you map it into a vector of numbers. And the model will actually pick up similarities between things that behave similarly. So here are some examples of training a skipgram model, which is a type of model, on text data. And so the model learns that the relationship between Spain and Madrid is roughly the same as the relationship between Italy and Rome. And similar things hold in the medical space, where you learn things about the diseases and the drugs that correspond to them. And so you can actually take cancer and you can look at the embedding for cancer, and then you can add a specific vector, which is essentially the difference between the drug and the disease on average, and you end up with, in this case, cisplatin. And similarly with the other drugs there. And so here is essentially an example of how that works on the full example, where each token basically gets embedded. And so the embedding is illustrated here in the right with just a vector of numbers. And then at each step, the input to the network essentially doesn't look at the words of the text. It looks at the embeddings, the vectors, the numbers that were learned. And those numbers are actually updated as part of the training. And so the final model that you produce will include the appropriate numbers in your embedding vectors. And so these things can be shared also across tasks a lot, because typically they encode something fundamental about the properties that are represented by those tokens or those words. And that can be used across different tasks. And then, so what normally comes out of TensorFlow is essentially the label that's the same type of label that you started with. We actually convert that internally to risk assessment, which is one FHIR resource that that is the most appropriate in many cases for this. We have some extensions in there, for example, for the prediction threshold and things like that. And we will open source the conversions for this in the near future. And this kind of goes back to how we would actually use this in serving, where you can imagine that you have a FHIR server, for example, that has some sort of trigger that, for example, for every patient that's an inpatient, once an hour, you're going to generate a bundle. And then that bundle will go out and get converted into a TensorFlow example. And then you have a set of models that you have trained for the tasks that you're interested in. And these models will run on these examples that are generated periodically and produce predictions. And then these predictions are turned into risk assessments and written back into the FHIR server. And so now you could, for example, subscribe to these risk assessments, and that would be a way, for example, to look at how risks for various patients are changing over time, maybe trigger alerts, or whatever you want. And that's just one way of using it. There could be other ways as well. But the only thing here that really would be different for different tasks, or if, for example, you had a marketplace or something like that for models, the only thing that really is different here is the model. And the model, if the model uses input, that's the same. And remember, for every prediction task in this framework, the input is actually the same because there's no hand-engineered features. It's just all the FHIR data in sequence. And so any model can run on this one type of example. So you can imagine a whole set of different models running at the times that they specify and in a very generic way. So like a FHIR store could do this. A FHIR server could do this, for example. You could just say, upload my TensorFlow model to my FHIR server, and it could work that way. And so to sort of step back, what we're trying to do here with open sourcing all this stuff and talking about it is we want to make it as easy as it became a couple of years ago to do machine learning on healthcare as it is to do machine learning on images, to apply the tools and technologies that have been developed by the community in ways that are useful for the applications that you are building. And with that, questions? All right. All right, Josh.
When you generate the examples that you pass into the model,
Yeah.
does every field from each FHIR resource make it into the examples?
Right, that's a good question. So almost every field. So certain fields do not. For example, ID fields typically do not because they're not going to carry any value. So there's a small short list of things that don't. So extensions, typically we don't copy them directly. So if you want an extension in the features, then we use profiles or something similar to profiles for that to actually get that data in as well. Yeah.
Early on in the presentation, you showed a arrow showing the unstructured or messy electronic medical record data to FHIR.
Yeah.
Is anything of that being open sourced on the Google page? Because that's actually, you know.
Yeah, that's that's a good question. It's one that we get a lot. So right now, no, but it's under active discussion, and we might at some point release some of that stuff as well.
Thank you for presentation. And how the quality of data influence the result? Because I don't believe you can push anything. You should have a lot of statistical data if you want it work, yes. But I know I bring you some patient record from Europe, yes, but you train it on United States.
Yeah, no, absolutely. So in general, for any machine learning tasks, when you do inference, when you do serving, you need to do it on data that looks statistically similar to the data that you train it on. And so, for example, you can imagine a data set that has nodes, and you train on that, and then a data set that doesn't have nodes where you try to do inference later, and then your model is going to be confused. And so if you switch domains like that, you have to make sure to do careful evaluation to see that the models actually are able to deal with it. And I didn't talk about that at all, but that's a somewhat involved step that has to be done in those situations.
And potentially I see maybe we can use machine learning to clean up the data, yes? Like looking for this.
Fundamentally, I think you're always going to want to do the evaluation, but I think there are definitely things that you can do to regularize your model and try to make it more robust to these type of situations. But without knowing which features are going to be available or not, or which biases the data will have or not in a new domain, it's hard to predict that. Yeah. All right. I think that's it. Thank you.